All right, so hopefully everything went good with 2.4. Now we're going to start 2.5, which is you are going to be able to implicitly differentiate. So we've been differentiating, taking the derivative, that is, with respect to x for umpteen times, or respect to t, and you didn't really see a couple things together at the same time, like taking the derivative of two different types of variables. And that's what we're going to be doing here. So explicit is what we were just doing, where we could take easy derivatives. Implicit means that I maybe can't get it into the form y equals all in terms of another variable. So I have two variables combined. Well, here, I could switch that guy and make him explicit, and then just do my derivative rule here. That's cool. Or I could do what I'm going to show you with the implicit. Here, I know this isn't a function, okay, but let's say I still wanted to derive, so it says functions. I don't really think all these are functions, sorry about that. But let's say I still wanted to find the derivative of this circle here. So if I tried to solve for y, I'm going to find out I get two different equations, so that's a little bit tougher. So in this case, we are going to want to do the implicit. Whereas here, can you even solve for y? You could try to factor it out, but then you're still going to have the equation in terms of y. So you cannot get y in terms of x. Like, it's just not possible here. So we definitely want to do implicit here. Now, if I can get it to explicit, sweet, makes life easier. Go for it. If not, then do the implicit, which I'm going to show you, so don't worry. Actually, just do it all on your own. I'm just kidding. Okay. How many of you are just sitting in your bedroom, in your pajamas, taking notes with Mr. Rose, having a good old time, eating popcorn? Okay, so implicit differentiation. So in this case, you can differentiate with respect to different variables. We're going to say usually with respect to x. Not always, okay? But it's usually with respect to x. A lot of times you're going to differentiate with respect to time, so like t or something. But find what you're going to do. So here, for instance, let's say that I just wanted to differentiate this part of the function with respect to x. Then when I take the derivative of that, I'm going to get 2, but I kind of have to say a little bit more. I have to say, hey, y'all, I took the derivative of y with respect to x. Whereas if I just took the derivative of 2x, and I said, okay, the derivative of that is 2, well, I took the derivative of x with respect to x, those cancel, and we just get 2. And that's what we've been doing. This is what we have seen. So now it's just when basically these two variables are different, I have to write this part when I derive. So then that's what we want to solve for. We want to solve for the derivative of y. So we get all those terms on one side, we factor, and we solve usually through division, which we will see. Okay? So again, this could be any variable that we are differentiating with respect to. But here, on the first problem, I see that I am differentiating with respect to x. It tells me right there to find dy of dx. So I am differentiating with respect to x. Okay, I could solve for y here, yes? So let's see, y to the 1/3 would equal 19 minus x to the 1/3, and then raise both sides to the third power. And then I could differentiate by using my chain rule. So this was how we would do this explicitly. Oh, sorry. Now, if I wanted to do it implicitly, I wouldn't go solve for y. So I'm going to leave it like this, and we're going to derive. So here I take the derivative, but I took the derivative of x with respect to x. Here I'm going to take my derivative, but I took the derivative of y with respect to x. And then 19 is 0, so it doesn't matter what the variable was, it goes away at 0. That cancels to 1. And now I want to solve for dy dx. So I'm going to subtract that part over. And divide by this guy. Those cancel. I can flip-flop a little bit. So this is what I would get for my derivative if I did it implicitly. Now, why do they not look the same? Because this still has a y going on in the equation. If I wanted to match them, then I'd solve for y and plug it in and see that they're the same. Alright, so let's look at this guy. Can I solve for y? Well, if I try to factor out a y, I still have another y. There's no way to just solve for y in terms of x. So I'm going to have to do implicit. And when I see my implicit, I see that I have a product rule here, and I have a product rule here. In the product rule, I'm going to take the first times the derivative of the second, but when I took the derivative of y, I took the derivative of dy with respect to x. Plus, I have the second times the derivative of the first, but I took the derivative of x with respect to x. So that's this first part. Now I'm going to move on to here. So I have the first times the derivative of the second. I took the derivative of x with respect to x, plus the second times the derivative of the first. I took the derivative of y with respect to x. So that's that second part. Equals, and believe it or not, this is one of the most common mistakes. The derivative of a constant becomes 0. Don't put -2 again. Alright, so all those dx's, they go to 1. From now on, I'm not going to write dx dx. Okay? So let's get this simplified up a little bit. So that's going to be x squared plus 2xy, x squared dy dx, plus 2xy plus y squared plus 2xy dy dx equals 0. So now I am trying to solve for dy dx. So I'm going to put all the dy dx's on the left, everything else on the right. Then I can factor out my dy dx. And now divide by all of that. And there is dy dx, which we tried to find. Woohoo! In this case, if I wanted to find the slope of a tangent line or something like that, then I'm going to have to plug in values of x and y. So I can't just have, like when x equals 1, I might have to go and plug it back up here to find what y would be. So I have to plug in x and y there, which is new. Alright, let's go to this next one. Why don't you try it? Pause me and then see how you did a little bit. So I cannot solve for y here, so I'm going to do implicit differentiation. In this, I have the product rule, and I have a chain rule. I'm going to start on the left. I'm going to do the first times the derivative of the second. Derivative of 1 is 0. Derivative of cotan is negative cosecant squared, but I took the derivative of y. Plus the second times the derivative of x, which is just 1, dx dx. Equals derivative of the outside, leave the inside alone, times the derivative of the inside. Well, the derivative of the inside is the little product rule. So the first times the derivative of the second plus the second times the derivative of the first, which is 1. Alright, I'm going to make this look a little bit better. Now I'm going to go ahead and distribute that negative sign y. And now this is what I have to solve for. So I'm going to move all of those over to the left and everything else to the right. And as I'm moving them over to the left, I'm going to go ahead and factor it out to save a step. So factored out of this guy is negative x cosecant squared y. When I bring this one over, it's going to be a positive x sine xy. So it's just kind of nice if you can do some things in one step. So then let's see, that guy stays. Bring these over. And now I can solve for my dy dx. Man, could I pull out a negative there? There's just a lot of negatives. What if I went ahead and distributed that negative down below? So maybe pull out a negative there as well. And then those both become positive. That looks a little bit better. Okay, now we're going to find the dy dx, but we're going to then evaluate it, so we're finding the slope at negative 1, 1. Alright, so let's go ahead and first find that derivative implicitly. Derivative of the outside, leave the inside alone, times the derivative of the inside. Derivative of x is 1, derivative of y is 1, dy